Now, as the guys at Monty Python say, time for something completely different. I'm going to try and take you through the process of how the jewellery industry is starting to adapt to and adopt the additive manufacturing process. In order to do that, I need to step back a little bit and give you a little bit of history about how we've arrived at this point. So this is me. I'm a lecturer at the School of Jewellery here in Birmingham. This is at my school, established in 1890, so next year we're 125 years old. We've been around a while and we've done a bit. I like this picture, which was taken in the late 1890s. Some of these kids in this picture are 12 and 13 years old. They are apprentices and they are doing part-time study at the school in the evenings after they've done a day's work. No collars, ties, and in homage I'm wearing a waistcoat to match them. It's a smashing working environment and we've got a lot of really good students, and the new term's just started. But also, as well as being a lecturer at the School of Jewellery, I'm the technical manager of the Jewellery Industry Innovation Centre. It's a department within the school set up in '97 to assist jewellery, silversmithing and metalworking industries to access new technologies and training. This is why I feel able to stand up in front of an audience like this and discuss the things I'm going to show you. The jewellery industry and digital technologies. After all, we're blokes who sit at benches and we use hammers and files and pliers. Where do we use digital technologies? Well, actually, we're early adapters. And what that really means is the jewellery industry has no hesitation in stealing somebody else's ideas. We're quite good at adopting what other people develop into our industry. And another key advantage for us is we have no qualifying standards. We're not like the aerospace or the automotive guys. The only thing we have to do is make sure the jewellery we produce is of an assayable standard. As an industry, we're long-standing users of computer-aided design and 3D printing. We've used it for 20 plus years. It's something we know, it's something we understand, and it's something that we're very good at using. As an industry, we're very adept at subcontracting and outsourcing. We don't need to have all of the technology, all of the expertise, all of the knowledge in-house. We're very good at putting it out to people who know how to do it better. But the artisan craft skills are still required. I heard a great phrase yesterday on another presentation. A robot is not a craftsman and an algorithm is not a designer. We still need those handcraft artisanic skills within the jewellery industry. If you can see the cross on this picture on this side, the cross was created using laser scanning, 3D printing, wire erosion, and a number of other fairly advanced digital techniques. But at the end of the day, it still needed a skilled jeweller and silversmith to put the thing together to make the final finished artifact. So what digital technologies do we use in the jewellery industry? We use CAD software. There are a lot of CAD softwares around in the jewellery industry, and here's just a small smattering of them. There's 5 there. They're about the 5 principal ones that we use. But we recently conducted a survey into the use of technology within the jewellery and silversmithing industries. The response to which CAD software do you use actually threw up more than 30 different answers. There's a lot of CAD software out there and a lot of people are using it in lots of different ways. When it comes to 3D printing, there are 3 principal technologies that we use as an industry. There's the solid-scape wax printer. All of these you can actually see out in the hall if you need to. This has been de rigueur in the industry for that 20 years that I've been talking about. Variants and versions of this machine have been around for a very long time. It 3D prints into wax that we can put straight through into the traditional jewellery lost wax investment casting process. A later comer to the scene then are the EnvisionTech machines, digital light technology. They again can produce really advanced, really good quality products that we can either cast or mould from within the jewellery process. And then more latterly, There's the 3D Systems project, which multi-jet prints into a wax-like material that is castable. All three of these systems are available within the Jewellery Innovation Centre, and we use them extensively to teach the students at the school what these technologies can do. But also we allow companies in the area to access these technologies to evaluate for themselves whether it's a technology they really want or need to follow up on. We're not selling anybody anything, we're giving away the knowledge. But there have been some recent developments in this world. If you've had time to look around these halls, you'll notice a plethora of home 3D printers that are extensions of a lot of the big manufacturing machines out there. And this is now starting to filter down into workshop style machines. So as part of the 3D Systems stable, there is their little Project 1200. This thing is no bigger than a shoebox. I'm hoping to get my hands on one in the very, very near future. The output that I've seen from it so far will work in the lost wax casting process. Then also you've got the new Autodesk machine, the Spark. I've been lucky enough to be involved in its early development with the guys developing this machine. Again, it's a workshop size machine. The 3D Systems project machine is about £3,000. The Autodesk Spark machine, they will sell for less than $5,000. Both are workshop adaptable if you have the CAD files to put into them. We also do a lot of laser scanning. Laser scanning is a very good way of capturing data that you can convert into jewellery items. But even in laser scanning, there have been some recent developments. We absolutely love this. 123D catch, another Autodesk thing. With this, you can take about 20 sequential digital photographs, feed it into the software, and the software converts it into a file that is printable. Absolutely amazing piece of kit, and it's a free download. White light scanning is starting to move across into the laser scanning area. It's bringing the prices down, and it's making it more affordable and accessible. But even beyond that, people are building home scanners using the Kinect off their Xboxes and Wii's and things. But let's get into what I really want to talk about, and that is the additive manufacturing of precious metals. It has a number of varying titles, some of which are listed there. But really what we're talking about here is the process of joining materials to make objects from 3D model data, generally by layer upon layer. As David said, what attracts us as jewellers to a process like this are those open geometric freedoms that it gives you. These are early examples that we got access to, produced by engineers, designed by engineers. They're titanium and produced on the industrial machines. But as jewellers, we were well able to see the potential that this technology was starting to offer. So which technologies are there out there that we're looking at for the additive manufacturing of precious metals? All three of these technologies can be seen in this hall. So there's the Concept Laser M-Lab. There's the Realizer SLM50. And then there's the Kuxengold and EOS M080. The concept machine, the M-Lab, is being used in the UK by a company called ES Technologies. They are producing jewellery items on it regularly. The Realizer is more a European-based machine used by a couple of companies in Italy. And the Kuxengold M80, I'm lucky enough that that's actually being used and operated in the factory next door to me. Just a brief video of the M80 machine. This is a machine that's been designed and developed from the ground up to be specifically useful within the jewellery industry. The jewellery industry uses precious metals, powders that cost, gold powders that cost in the region of £35,000 a kilo. You want to protect them, you want to look after them, you want to be able to control them, and that's the way this machine's been designed. So it has an 80mm build plate. There's a module processing chamber, so instead of flooding the entire chamber with covering gases, it's just constrained within that jam jar. The powders are contained within a hopper, so everything is self-contained. We're not spreading vast quantities of expensive powders all over the machine. And the machine just runs backwards and forwards, lays down a layer of powder, strikes the laser beam across it, and starts to build the item. Now when it gets to the end of the process, you want to be able to extract the things you've built. So what these guys have done is they've inserted in an extraction cartridge. You simply lift it up into this extraction cartridge, all of your gold, your build item, extract it from the machine, turn it over, save your gold into a sieve for reprocessing to the next build, and you've got your finished items ready. So let's have a look at some of the work that my students have done over the last couple of years. You can see here some examples of their work, laid out in the CAD file, ready for processing in the machine. The red pieces you can see underneath are support structures that have been generated by the software. I'll come into those support structures in a little bit more detail a little later. We are teaching our students the principles of additive manufacturing and designing for jewellery. We believe we're the only school in the country, probably in Europe, that's actually specifically teaching students to design for this process in the jewellery world. So once these files have been fed into the machine builds them using the process you've just seen. And these are actual student jewellery parts coming off the machine. As you can see, there is quite a lot of powder flying around there, because this isn't off an M80. But a simple quick clean up, a bit of plastic shot peening, and they're starting to look like proper pieces of jewellery. And there you can see an assortment of them. After they've been taken off the plates and the support structures removed, this is the point at which the student becomes a jeweller. They now start to pick these up. They apply files, they apply solders, they apply stones, and it starts to turn it into a piece of jewellery. But it's a piece of jewellery that can only really be manufactured using this process. So let's have a look at some specific examples. Charlotte's earrings, plated in red gold, some earring tops added, and it actually starts to look like a nice intricate piece of jewellery. Those of us from the jewellery world, if we study this piece closely, we would realise it would be difficult to impossible to actually cast using the loss fast casting process. I could build it on a wax machine, just about, but the caster would really struggle to get the metal to flow through all those areas. Hannah's ring, the wonderful cage ring, again an excellent example of taking advantage of what the technology can do. Again, it would be, I could probably just about print it, but it would be extremely difficult to cast it. And some nice intricate work from Joe, and we're going to come back to Joe's work in a moment. Sophie's work was interesting. Here's a CAD file. Notice the two carriers at the top of the pendant where the stones go. Those holes were left there because this pendant spins within that top piece. Built in one piece, a moving piece, and the powder that was trapped is just allowed to fall out through those holes, and that gives us a fully rotational piece. And then you get Willow's wonderful piece again, hugely complex and difficult, taking advantage of what the technology can do. This is Joe's work again. Joe came up with this wonderful bangle Only problem was, it was too big for the build plate. So we scratched our heads, fiddled around a bit, and we came up with a solution of chopping it into 3 parts, turning them on the side, which extended the build time a little bit, and printing them on the machine. And here you can see the actual parts built on the machine, and again, you can see these support structures that are required to hold everything in place. Taken off the machine, soldered together using traditional jewellery soldering techniques, which gave us a nice finished piece, and this guy's won awards for this piece. Again, difficult to produce using other traditional jewellery manufacturing processes. As jewellers, we've had a number of lessons to learn about adapting to and adopting the additive manufacturing process. Software, we were pretty good with software. We know how to design 3-dimensionally in CAD. We struggled a little bit with some of the machine software, which does the automatic processes of adding support structures. That's been a fairly steep learning curve. Support structures I've just covered. Finishing and polishing. We finish and polish everything we make. David touched on surface finish and surface quality in his presentation. The surface off these machines these days, in precious metals for certain, is only slightly, very, very slightly rougher than your average cast surface. So we're very good at polishing back the jewellery we've cast. We're very good at polishing back additively manufactured goods as well. And of course, we've had to consider the business model and the supply chain. This is a completely new manufacturing process, and as an industry, we've got to think how we're going to adapt to it and use it to sell goods. I'm not going to cover that too much in this presentation because there just isn't enough time. Support structures. Support structures are there for a reason. As you saw in the little video clip, there's this sweeping motion that moves powder across. That's a fairly aggressive action, and the piece that's being built has to be held quite sturdily in place. It's also a hot process. That laser beam is creating tiny little melt pools of molten metal that bond to the layer next to it and to the layer below it. They have to be held there. While they're in that fluid state, they have to be held in place. It's a hot process, as I said, and that heat has to be drawn away. Otherwise, you get distortions in the process. So the support structures need to be there to hold everything in place. The spoons on the right, the support structures are quite aggressively placed. There's an awful lot of them facing downwards. It would have been easier to build them vertically. There'd have only been a much smaller number of supports, but it would have been far more susceptible to possible damage during the process and would have taken 10 to 15 times longer to build. So it's a judgment call about orientation of the part. The rings are a much better example. They're at the magic 45 degrees. 45 degrees is about an optimum angle at which, if you're building something, it will be self-supporting. But we as jewellers, we're used to sticking extra bits onto our jewellery. In the casting process, we create an item, let's say a ring, and then we stick a sprue on it. We've got to somehow introduce the molten metal into it if we're going to cast it. So adding extra parts to our jewellery and then taking them off afterwards is not an issue to us. It is something we do on a regular basis. And we've discovered it is actually nothing to be feared. Here you can see on the left an 18-carat watch case built on the Cookson M80 in 18-carat gold, and you can see the close-up detail of the support structures that were there. You can also then see the watch case after it had been removed and polished, and the watch case in the finished watch. So what have we done as an industry? We've worked together with people who have these machines, and particularly with Cookson Gold, as I say, because they're in the building next door to me, and explored some of the possibilities that this technology offers. Some wonderfully complex pieces, some interesting stuff. You can actually build gold chainmail, flexible materials. The wedding ring is quite an interesting exploration into what this technology can do. You can make hollow items, quite simply. You just simply leave a small hole in the item so that you can shake out the surplus powder that's trapped inside, seal it shut with a laser welder, and you have a finished hollow item. Except that, just because you can do it doesn't always mean you should do it. If somebody puts a wedding ring in your hand that's hollow, that weighs about a third of as much as a third of what you expect it to weigh, it doesn't actually feel good. It's got no heft. It's got volume without the mass. So there are plenty of applications out there where making things in a hollow form are definitely applicable. For instance, the watch bezels. If a watchmaker is trying to create a watch with a gold watch bezel, and it's got something like 250 grams of gold in it, that's going to become by the time that it's gone through all the processes and all the markups, that's going to become too expensive for him to sell. If he can take 150 grams of gold out of it by making it hollow, it then becomes a more attractive item and more cost effective. There are also other things the jewellery industry are very interested in that this process allows. It allows personalisation, individualisation, customisation, and this is the one we really like, co-design. This is the process where you, as the consumer, go into their website and design your piece of jewellery for yourself. This speaks back to my statement about a robot isn't an engineer, and neither is an algorithm a designer. What you're actually doing is manipulating somebody else's design within an algorithm that's been preset for you. This is a video from a website, and you as the customer can manipulate this ring. You can manipulate it as a bangle, as a ring, as a number of different pieces of jewellery, just by simple movement of sliders. In live real time, then the software also tells you the price of what you're doing and its probable delivery. Now, when you're the consumer and you're designing, in inverted commas, your own ring, you're starting to invest emotion, you're investing time, you're investing some of yourself into the item you're designing. And that then becomes a very attractive proposition for what is a fairly expensive manufacturing process. This process isn't about making things quick, easy and cheap. It's about making different things in a different way. Here we've got some more examples from the Cooks and Gold guys. Another spinner. This is 18 karat red gold. And again, the bottom part, this part rotates around the top part with no sub-assembly. You can see the support structures that were used to hold it all in place. Take those away, clean it up, give it a polish, and away you go. And again, you can do some really, really complex parts using this technology. These beads again are 18 karat red gold, but because of the shapes that have been created on them, they are self-supporting. It's got the absolute minimum amount of support on the bottom that's needed. We love these eggs. The eggs are absolutely brilliant. You see the small holes in the top. Get the powder out, you've then got a fairly substantial looking piece of 18 karat gold jewellery that hasn't got the mass. This is something where making it hollow really is applicable. And we're also very impressed with the amount of detail you can actually get onto the surface. So within the Innovation Centre, we're actually part of something called the Precious Project. It's a technology strategy board funded research project to demonstrate the viability of the additive manufacturing process in precious metals. And if any of you want to catch up on it, the details are there. 5 partners in it, ourselves, Cooks and Gold, Future Factories, which is a one-man business, a guy called Lionel Dean, who's a designer who knows and understands how the additive manufacturing process works, a finishing company who do the polishing, and Delcam, who are doing a lot of work on the software and the support structures. So this is a project called the Ojo. Any Spanish speakers? Yeah, the Ojo. Being Brummies in English, we call it the Ojo. Simple CAD design. Support structures are added, fed into the machine, which starts to print the piece. So this is us beginning to extract it from the machine. 18 karat gold, note the surface on it. We simply break off the support structures with a pair of pliers. Polishing, as I said earlier, this is what we're good at, and this is what the engineering, aerospace and autospace guys ought to come and learn from us. We use a process called stream finishing. That bowl that you can see there is a centrifugal bowl with a media within it that is whizzed round at extremely high speed. We mount the piece in a turning spindle and we immerse it into the media. It can be wet or dry media, high speed centrifugal finishing. We found for this particular project the best results were achieved using a small 1mm diameter high density ceramic media, tiny little beads that would get into all the inner surfaces and all the inner crevices. We're using this technology to create hugely complex parts with lots of inner surfaces. We needed to investigate ways of actually polishing those inner surfaces. The bowl wabs round at 60-80 RPM, and the part being held in the media is it's not rotated at a high speed, it's just rotated quite slowly. If any of you have been involved in mass finishing, one of the problems is that the media will have a tendency to conglomerate within the part. If you put it in a vibratory bowl or in one of these centrifugal bowls on its own, after a while the process will cause the media to collect in the centre, so the inner parts don't get worked and activated. By actually keeping it turning and rotating, you actually polish the inner parts of it. So high media pressure and high speed differences make it suitable for intricate detail. So here's a part that's been in the machine for about an hour. You can see from the earlier pictures the surface is starting to come back, starting to polish up quite nicely. Here it is after its final process through the bowl, before we actually do proper jewellery hand finishing and polishing. And here's the finished piece. And for those of you who are not Spanish speakers, ojo is Spanish for eye. A little advertisement. In 2015, we at the School of Jewellery are starting a new master's degree course into innovative metal manufacturing techniques and the business structure behind it. A lot of this course will be about the additive manufacturing process, laser-based technologies. So it just remains for me to say thank you, just in time. And I'll leave you with a final picture that shows that jewellers are not all fluffy and kind and nice. We're actually quite brutal. Thank you.